Thanks for everyone who's joining us online. It's my great pleasure today to introduce our seminar speaker, Professor Peter Tuthill. Peter completed his bachelor's and honors degrees at UQ and ANU before going off to Cambridge, where he studied astrophysics, worked on astronomical imaging and stellar interferometry. He then completed a postdoc at Berkeley under the supervision of Charles Townes, who you might know as one of the inventors of the laser. And then he moved back to Australia and through a series of fellowships took on a professorship here at the university, where he is in charge of several large efforts. He was the director of the Sydney Institute for Astronomy from 2010 to 2015. And now he's in charge of multiple large astronomical projects with excellent acronyms. So the Georgia State Center for High Angular Resolution Astronomy, CHARA, at Mount Wilson, the European Southern Observatory Very Large Telescope Interferometer, the VLTI. And he is, I think, the only person I know with an instrument on the James Webb Telescope. So his research interests are in stellar astrophysics, optics, and advanced instrumentation. And today he will tell us about the TOLIMAN project, which is a search for Earth-like planets at our nearest stellar neighbor. Please join me in welcoming Peter. Thank you.
So I was told this was a pretty informal crowd and an informal kind of venue and a talk. So just jump in with questions, or don't have to wait till the end. And if it helps sort of ease the social boundaries here between the physicists and the astronomers, my brother's actually a PhD engineer. So I had a precipitous career decline, but he managed to see the true path. In fact, he works at the ATNF, where we were just talking about. He's a radio engineer working on the radio telescope arrays there. It's kind of cool thing for your H-index as well, because another astronomer called Tuthill has got to be the same guy, right? So all his papers end up getting credited wrongly to me, which is good. So I'm talking about the TOLIMAN mission. We've got a very cool mission patch. In fact, I don't think we've brought any merch, but Connor can get you a sticker. And we've been able to poach some of your amazing graduates. Connor's here, of course. We also have Adam and Grace. Adam's sort of peripherally involved, but Grace is very much working on TOLIMAN. You'll see some of their work later in this talk. We have had and still do have quite a lot of connections around the world. We work with people at NASA, and I somehow forgot to put their sticker up here, but Leiden Observatory, Leiden University in the Netherlands, JAXA, Japanese Space Agency. So I should sort of spread the credit around a little bit. And this whole enterprise came from a very unusual start as an academic. It sort of like was this trapdoor that opened in my life and dropped me into a world that was very unfamiliar to me, because I answered a call for a white paper from a billionaire. His name is Yuri Milner. This is Yuri. And he funded a thing called the Breakthrough Prize, which is in open competition to be the Nobel Prize, and you compete by actually offering more money. So the Breakthrough Prizes are deliberately a higher value dollar amount than the Nobels, and they have this big thing every year. In fact, the Breakthrough Prizes are funded by a number of what our university administrators would call high net wealth individuals who they have dossiers on. So, in fact, also Zuckerberg and a bunch of brand people you probably know the name of. Yuri wasn't happy with just this prize, so he also started direct funding of science. And there's this funny meld between where the prize institute ends and the initiatives end, but the initiatives are his gig. And one of the things that he put up for an initiative is a thing called Breakthrough Starshot. And this is audacious is one word, or sort of batshit crazy is another word, but it's a very, very ambitious idea to launch a extremely high velocity probe, and we're talking about a quarter the speed of light, to get to Alpha Centauri, which is the nearest star to Earth, apart from the sun, of course, to get to the nearest star system to Earth in his lifetime. So that was the sort of, I want to see the results before I die kind of thing. And, it's 4 light years. So if you go 10% of the speed of light, that's 40 years. That's too long. So you need to go significantly faster than 10% of the speed of light. And if you do the equations, the general relativistic equations, you really want to economize back on the mass. So the mass of this thing is something like 1 gram. And even then it's carrying, I forget, there are these kind of analogies, but it's more energy than an entire aircraft carrier going at 500 kilometers an hour or something, all dumped into 1 gram object. So this is incredibly audacious, and I kind of like this for one particular reason, and that is that it's shown that it doesn't defy the laws of physics to do this. You can actually build an on-paper technology that can take you to the nearest star systems in 20 years. It defies all of the laws of engineering, and forget about the laws of economics and politics, but you can actually do it on paper. And it's already a cool thing, I think. So if you're going to spend $1 trillion on a technology to get to the nearest star system, you know, it's an awful expensive bus ride. There better be a bus stop there that's worth getting off at. So these guys naturally asked the question to the astronomers, well, what's the planet situation like in Alpha Centauri? You know, is there a cool habitable mass, you know, Earth analog planet in this system? And we don't know. So hence, I answered a call put out by this foundation for a technology that was capable of delivering that answer. Is there an Earth analog, potentially habitable zone, 1 Earth mass planet orbiting our nearest star system? So this was the challenge. It's basically, and lucky for us, and we'll come to why it's quite so freaky lucky for us, Alpha Centauri's a binary, it's got 2 stars. So we got sort of 2 bites at the cherry, and both of the stars here in the Alpha Centauri system are more or less sun-like in the way astronomers would define them. So an Earth-sized rock going around these things would be called a true Earth analog. That's sort of the holy grail. An Earth-like planet in a temperate orbit around a sun-like star. We've only got 1 data point for life, and that ticks all the boxes possible. So that's sort of like the most sort of exciting piece of real estate that an exoplanetary astronomer can possibly hope to find. But it's pretty embarrassing. We don't actually know. So I've just got this. This is a sort of a voyage that it would look like. This is the dash cam from Starshot, sped up to a few seconds. So we just passed Proxima Centauri, which is a red dwarf star. It's a triple. It's actually bound to this system, but it's very distantly bound. So in the heart of the Alpha Centauri system are these 2 sun-like stars, Alpha Centauri A and Alpha Centauri B. They orbit each other in about 80 years, and they're both kind of would mark ideal outcomes for if there was a, you know, if there was a planet there, that would be great. So the obvious, when I'm giving this talk in public, the obvious thing is, well, you know, we found Mars and we found Neptune and we found Jupiter. We did that by sort of going out and looking up. Why don't we just go out and look up? That's the obvious way you find planets. So this is an image that the Cassini spacecraft took in our solar system of Saturn. It's one of the most famous astronomy images of all time, probably a stunning image, really. And this appeared on the front. So the spacecraft has flown to the far side of Saturn, is looking back towards the sun, and you see Saturn in silhouette here. This appeared on the cover of National Geographic. And when it did so, there's this little fleck out in the rings that the artists at National Geographic, they airbrushed this out because they thought it was a bad pixel. And they actually airbrushed out the moon and the Earth. You can see if you zoom this up here. This little tiny fly speck here is the Earth and the moon. And that shows you, even when you have the world's best, what we call a coronagraph, a thing to block out all the glare, massive big gas giant planet, and your planet is still separated a long way because you're still very close to the Earth here. It's easy to mistake the Earth for a bad pixel in an image. Going out and looking up is very, very, very hard. You get about 1 photon from your planet for every 10 to the 10 photons you get from the star. So you have an insanely difficult contrast problem. You could liken it to trying to see a glowworm crawling 1 millimeter away from the arc lamp of a lighthouse from about 10 kilometers out to sea. And you have to do that entire exercise through the Earth's atmosphere, which then is like doing it from the deck of a rolling ship. So It's very, very, very hard thing to do, although not impossible. A lot of my work in my group is trying to address this technical problem separate from TOLIMAN, but can we actually make direct images? This is called direct imaging. And if you want to directly image a planet, there are almost no discoveries made of exoplanets this way. So here's our target. Here's our star system, Alpha Centauri A and B. It's a binary. It goes around in about 80 years, as I said. The apparent orbit is quite edge on from our perspective. And at the moment, it's going through this moderately close approach in the binary orbit, which makes some astronomers makes problems for some of the astronomers who are trying to do these kind of measurements. Close stars in the sky can cross-contaminate each other and they mess up each other's spectrum and slits and things. We'll come to that. So good news for us, there are two habitable zones, one around Alpha Centauri A, one around Alpha Centauri B. And even better news, a planet were it to exist in either of those habitable zones, temperate zone, where the liquid water can exist on the surface, is the way we define that. So the right distance, if you're too far away, you freeze, too close, you bake. There's this concept we have of the habitable zone. Those habitable zones are dynamically stable. In other words, in a binary system, if you orbit too far outside this red line here, then the binary will throw you out and you won't be able to have a stable planet there. But lucky for us, the habitable zones here are stable dynamically over cosmic time. So we're looking for an Earth mass rock in either of these green bands here. And there are really two techniques that astronomers use to affect this kind of measurement. One is transits, where the planet happens to pass across the face of the star and you get a little dip in the light. That only happens when you get very lucky. So the planet has to have its orbit exactly in the coplanar with the Earth, which is some random orientation off in the galaxy. So the probability of that is far less than 1%. We've already looked. It doesn't happen for us for Alpha Centauri, but that doesn't rule anything out. It just says we didn't get lucky that time. So transits are a technique which work really beautifully well when you've got 10 to the 11 stars in the galaxy. It's not at all effective when you're asking a different question, which is there a planet around that star? One technique that could do that is the second most effective technique that astronomers use, called Doppler radial velocity. So this is a technique in which the presence of an orbiting mass drags the star itself. And what we witness is the star moving in the line of sight, gradually towards us and gradually away over the course of a year. This is simply a reflex motion. We'll come to why, but Doppler radial velocity is also, basically it runs into a noise floor that I'll come to, and you can't get down to one Earth mass. And we've already proved that there are no massive planets in the system from Doppler radial velocity. There's no Jupiter, but we can't get down to below a noise floor. I'll talk about why in the next slides. So my mission, in fact, is based on still a third technique, which is sort of the ugly duckling in astronomy for finding planets, which may suddenly become very fashionable because there are new missions that are about to dump high precision data that'll empower this technique. But it's a thing called astrometry, which is just measuring the location of a star in the sky. Ultimately, it's like anatomy in some sense, in a physiological analogy. So whereas everything in the sky at some degree of precision, if we were an alien civilization trying to discover whether there was planets in our solar system, we might look at the sun. And if we happen to have a pole-on view of the sun, we would witness the sun doing a funny wobble on the sky. If we had precise enough measurements, we would see the sun getting dragged around by its own diameter a little more. So each of the dots on this locus here are at different dates. You might see some of them labeled. So every sort of 10 or 20 years, the sun gets shoved around by something we can't see. We infer that something shoving the sun around must be planets in the sun's environment. And in fact, this is almost all due to Jupiter. But Overlaid on this is also Saturn, pushing it at a different rate, and Venus and Earth. The ripple that would be imposed on this locus by the Earth is tiny. It's much smaller than the line type on this plot. So there would be a tiny 1-year ripple of the sun wobbling back and forth. It's a very, very small number, but it's real. If you had precise enough data on astrometry, you can get to the presence of planets. Note the planet can't run and hide. There's no luck involved. If there's a planet there, you'll find it if you have good enough data. So in fact, for nearby stars like Alpha Centauri, this signal, it turns out, is probably the one to go for. It's the signal to noise that we can get from this measurement is superior to any of the other techniques we have. I mean, it's kind of an embarrassing question that Yuri posed to the astronomy community here. This is our nearest star. Is there an Earth mass planet there around our nearest neighbor? We have legitimately no idea. There could be 2, there could be 10. We have really, astronomers don't know. You see all these catalogues of planets published, and there are thousands in those catalogues. Those are all times when we got lucky, pretty much. So they're not times when we were clever and we're actually able to discern whether a given star has a population of planets or not. So we're good statistically, but we're very poor on individual cases. And the good thing about this technique is that it gets us to this holy grail, these true Earth analogues: Earth mass planet, temperate orbit, sun-like star. So this is the plot that sort of, if you're an astronomer and you want to figure out how you're going to make this measurement, this is the sort of plot that might sell my mission to you. What I've done here is I've started with dim red dwarf stars, and I've gone up what astronomers call the main sequence to yellow-orange stars like the sun, and then up to hot blue stars. So generally these are massive blue stars, and these are dim small red cockroaches that nobody cares about. In fact, Proxima Centauri is one of these down here at the red end. So if you put an Earth mass rock around one of these and you insist that that rock is warm, not baked too close, not frozen too far away, for the red ones, you've got to cuddle up close to the warmth, stay warm. For the blue ones, you want to get away from the heat. So the blue ones have big, wide, slow orbits, and the red ones have little, tiny, fast orbits. Because the red ones have little, tiny, fast orbits, they oscillate a lot, so you get lots of cycles. And also, even more important, they actually drag their host star around quite rapidly because they're close in. So you get a very large signal on that radial velocity. The Doppler radial velocity is very effective here. So if you want to find planets around M dwarfs, radial velocity just booms up here. You get 80 centimeters per second. So that you're measuring the star moving forward and back over the period of weeks or months at a 1 meter per second level. It's pretty amazing when you think about it. We're looking at a star in the sky and we're saying how fast is that going to centimeters per second? Sort of better than a police radar gun, really. But you can see the problem with radial velocity is by the time we're out here in our Urey-Milner's sweet spot, we're not interested in red cockroaches. We want Earth analogues. This thing's dropped down here to like less than 10 centimeters per second. The noise floor, nobody's really built a spectrograph that's better than about here. So 0.5 meter per second is about where that technique claps out. So everything after those red dwarf stars is not accessible by this technique. On the other hand, if we look at that wobble on the sky with astrometry, we find that the signal to noise goes very differently. We get larger and larger signals from astrometry according as the planet's in a habitable zone of a hotter and hotter star. And it's funny to understand why, but because the actual deflection you get, even though the red dwarfs are moving very fast, it's a very fast oscillation, so they don't actually displace very far because, you know, the orbit's very rapid. You get a very fast but very small oscillation of the star due to the reflex motion of the planet orbiting around it. The Earth around the sun, on the other hand, you know, stays over in this arc for 6 months, so that the sun moves more slowly, but it gets dragged a larger distance. So the actual gravitational deflection imposed by an Earth mass planet rises according as you place that Earth mass planet around warmer, hotter and hotter stars. So for us, what we care about are these ones in the middle of the diagram here, the sort of solar analogues. And if we look across here for something only 1 parsec away, which is where Alpha Centauri is, we're getting this deflection here of 2, 3 micro-arcseconds. Looks really healthy. I'll tell you that the fundamental noise floor for astrometry is down about here. We have a fundamental noise floor of about 1 micro-arcsecond due to the intrinsic noise that the star gives us. So basically, all of this is fair game. It's all signal noise of many compared to fundamental noises. But that's only that's only the beginning of the journey. Of course, you've got to then build an instrument capable of making the measurement. So I started this by proposing a 30-centimeter aperture space telescope. And being a physicist, I'm used to the spherical cow in a vacuum approach where everything's perfect. So if I have a perfect telescope on a perfect day with no noise from any other process, I better make sure that it works against photon noise, because there's always going to be photon noise. That's the statistical arrival of photons. So what we're about here is we're trying to register an image on a sensor. How well can I locate that image? And I need to register that image very, very precisely because I want to watch it wobble over 6 months. And if photon noise was the only thing I had to beat, I had a perfectly stable sensor and I had a diffraction limited telescope of 30-centimeter aperture, I need to get to that number I just showed you. I need to get to 1 micro-arcsecond. That's the Earth dragging the sun. In fact, it's 2. It's the value of the Earth dragging the sun around. So I need to be about where this solid line is. So this tells you how long it would take me to integrate. Given fainter and fainter stars, I need to take longer and longer integrations. And you can see these big numbers here. It's a log scale. It goes up to a year at the top. But for Alpha Centauri A and B, they're very bright stars. We use voodoo units in astronomy, but Alpha Centauri A is 0, and Alpha Centauri B is 1, or 1 and a bit, which is actually fainter than 0. So you can see we get there in minutes. There's enough photons there to do this measurement easily. But the problem, if you have a camera and you're looking at something and you want to see whether it's moved, you need a reference on that frame. Unless you can keep your camera perfectly stable, which you never can, there's going to be vibrations. You need to measure that location of the star with respect to some fiducial points. You need a reso dots or something on your sensor. And those dots that you measure the location with respect to are background stars. So you measure Alpha Centauri sitting there in the sky, and you look at all the stars around it, and you want to see it wobble. But the background stars are pretty faint. Alpha Centauri is super bright. You're going to have background stars out at 11, 12, 13th mag. These are voodoo astronomy units, like I just said. That's a factor of sort of 100,000 times fainter than the star that you want. So that in order to make this mission work, I would need up here, I'd need just 3 or 4 months, maybe. Well, in fact, the brightest background stars are about 14. So I need about a year of time, of integration time with a perfect telescope just against photon noise to register this location that I need on my sensor. And if it takes me a year to do it, I'm sunk because it's wobbling every 6 months and I need to register that 6-month wobble. And even then it would, so now I need like a 2-meter telescope in space, and then I need, $500 million. But there's a trick here, and you might have already seen it. Alpha Centauri is binary, and Alpha Centauri A and B are both up here at the bright end of town, right? So if I don't care about my background stars, I don't care where my sensor is pointing, I only measure the separation on the sky of A and B. If A has got a planet that's wobbling and B is, so I can use B to reference A, or alternatively A to reference B. And then I make a relative measurement, and I just bought myself out of a world of pain and a very expensive large aperture telescope. So if we now limit our, this is the sky, the stars in the local neighborhood, out to, this is the local volume of space around the Earth. out to 10 parsecs, which is sort of considered our sort of neighborhood. This is how large a signal you would get if there were a planet around a given star. And you can see Alpha Centauri A and B, because they're very close and because they're sun-like stars, we get this very healthy 2 micro-arcsecond wobble on the sky. And apart from these blue ones, which I won't go into too much, there's really not much else in town within a factor of 5 of it. There's a couple of other ones here, Tau Ceti and Epsilon Eridani, we can come to. But my technique doesn't work on almost all these stars. I need a binary. I need to register one against the other. So if we restrict that diagram to only the binaries, we find basically we've just got one good target and then a bunch of also rans here. There's a few other targets that are a factor of not quite 10 times harder, but Alpha Centauri A and B, almost like God put them there just so we could do astrometry on them. It's a binary, it's close, very nearby, it's an Earth analog system. In fact, if you run history forward or back by 1 million years, we never have a sun-like star this close. It's sort of unusual. We would normally just have some of those swarming red dwarfs, which are very, very common in the galaxy. We live in an unusual epoch that we have an Alpha Centauri in our skies. So we're starting with some astronomy innovations, and I'm sorry it's gone. I'm going to go to engineering later, but we observe these binaries, and that buys us out of a lot of expense and a lot of pain. In fact, when you're measuring an angle on the sky, we're measuring an angle here of only like 5 or 10 arcseconds, and we're looking for a 1 micro-arcsecond wobble. If we were trying to measure that by registering it against background stars, which are 50 arc minutes away, most errors just accumulate with angle. If you are measuring a quantity and you have to measure it over a larger angle, you'll normally buy in more systematic error over the larger angle that you're measuring. So we actually buy another factor of sort of 20 or 50 just by the fact that we've got a narrow angle measurement of a very, very small angular deflection. But there's a catch to this whole strategy. We've only got a binary on our sensor, 2 stars. If it changes at all, if there's a wobble that we witness, we don't know if that came from the stability of our telescope or if it came from the actual sky. We need to fly a physical object aboard the spacecraft that acts as a ruler. And that you don't have to do if you're using the natural ruler provided by the galaxy or the background stars. So we get out of a lot of problems, but we buy a very, very tricky engineering challenge. How do we fly a ruler aboard the spacecraft? So this is my daughter. I've got her roped her in to help with my talk. If I wanted to measure the size of something, but I'm forced to do it in an optical system, that's easy to do if the optical system's perfect. But we have an optical system whose errors, even with the most stable materials, will be 10,000 times worse than the measurement precision you need to make. We'll come to how crazy difficult this measurement is in a minute. But let's suppose I got my daughter to hold that ruler up herself, and then I measured I didn't measure her size by looking at the size of the image. I read the size of the image off the distorted ruler that she's holding up. Then I would get the errors in the signal are now common mode, right? If there's a bendy mirror, then you'll get a bendy ruler, but it'll bend in exactly the same way. So there's an optical principle we can fold in here. We can make our errors in our signal common mode. And we do that with a thing called the diffraction grating. So our task is to measure the separation of a binary star on the sky. We have an optical system. Through a perfect optical system, we could just measure the separation of that binary on our sensor. But we have this imperfect optical system, and any measurement we make in our sensor will be almost degraded to the point of pointless. But let's suppose instead we put one stable ruler. In this case, it's a diffraction grating. We put that right out the front. The first thing the starlight encounters is a diffraction grating. Diffraction gratings create side lobes. So that'll split the beam into 2 side lobes and a primary beam. So a star will now appear to have 2 companions to it. And these companions will be dictated by the cadence of our ruler, our grating. But we're looking at a binary star. So the binary pair will also have a pair of side lobes. And instead of measuring the separation of our binary, we throw that away. We don't even try to measure the separation of our binary. We simply witness the fact that those two side lobes happen to coincide on the same pixel. So if we do that, and then we put it through a distorted optical system, we'll get it wrong if we measure the separation of our binary. But if we still witness that these two speckles lie, or the side lobes lie on the same pixel, then it doesn't matter that our optics was distorted. So we've just collapsed all of the errors in this optics into the requirement for a very single high stability element at the front of the telescope. And it has to be a very, very, very high precision measurement indeed. And I've sort of got these, we'll come to why our image looks like this, but this is a simulated image of the sensor for the TOLIMAN telescope. That's just the pixels on the image plane. That's the middle pixel. That's the silicon and some magnification, the plate boundaries. And there's actually silicon atoms on the sensor. So that red dot is the 6 month deflection of the image as it gets dragged around by a planet. It's much less than the atoms on the sensor. So it's sort of, I liken it a little bit to the challenge of LIGO. This is a slide I don't show to funding agencies, by the way, because it looks impossible when you see this. So over 6 months, we've got to register one image, moving to the other one by much less than one atom on the sensor. That's what 1 micro-arcsecond looks like. So we leverage that idea I just sort of tried to convey about a ruler out the front of the telescope. My first thought, because I've done this for some bunch of my career, was to do a thing called an aperture mask, which is basically just a plate with holes in it. And if you have a plate with holes in it, it turns the image created by the telescope into a quite complex pattern. And we see all of this sort of flowery diagram here. That would be the image produced of a binary star made by with a plate like that. So my thought was, well, I'm going to make this plate out of something like, invar that just doesn't move, and I can measure it really well, keep it really stable. That's my ruler. And then I want to measure the separation of this binary in my image plane. And of course, if I do this by measuring here in pixels, I get the wrong answer. But if I count how many fringes there are between those two stars, if my telescope distorts or the focal length changes, then the fringes will breathe because the fringes go through the same optical system. So if the fringes breathe and the actual size measurement you want to make breathes as well, it's made your signal in your error common mode. It's got rid of your errors. So that's the kind of principle we're going for here. The problem with this particular idea was that diagram's a filthy lie. That's kind of put on a log scale. But the actual diffraction created by a mask like this on a linear scale is not much. So all of that lovely patterned ruler on my image plane really doesn't have enough photons in it to make the concept viable. Principle works. So I now needed a way to make a ruler to spread the light from the star out into this diffractive ruler. But I needed a lot more messy point spread function than I was able to create, even by boring holes in a pupil. So if you're an optician and you really, really want to mess up a telescope point spread function, you can't go past phase. That's just a little tip from me. So if you want to have the world's worst point spread function, what you do is you grind the mirror down so that it interferes destructively across steps. So what you have to understand by this telescope mirror here, wherever you see black, I've ground the mirror down by half a wave so that the wave, the starlight that lands on the black parts will interfere destructively with the bits landing on the white parts of the mirror. So it's a complicated featured mirror, but it has this amazing effect. It turns the point spread function of the telescope into an absolute pizza. So we end up with these really sharp, really messy, diffracted scruff everywhere, speckles. So we actually no longer even have an image of the star. We just have this very complicated, large diffractive pattern at the focus of this telescope. And so now my task is to measure how many fringes there are between Alpha Cent A and Alpha Cent B over this diffractive pattern. So I'm stacking up some of the innovations that power the mission. We have these astronomy innovations. We're looking at binaries. We're looking at a bright binary, which buys us out of that big telescope requirement. And now we've got an optical technology that buys us out of requiring a crazy stable telescope. All we need is one crazy stable ruler out the front of the telescope, and then we can tolerate a telescope that is a real mechanical structure. It'll bend, it'll change temperature. Another good thing about this is that pattern you saw spreads the light over many pixels. And if you ever talk to information theory people, they love it when you spread your information that you require over a large number of samples. It gets you out of all kinds of systematic noise processes and flat field noise and things like that. So I was all happy, and at this point I'd already been funded for a phase A feasibility study, and I thought it was all going to work. And I told, this sort of slightly scary Russian billionaire that I was going to actually answer his problem for him. And then I woke up in the dead of night realizing I had made a massive blunder. And that is that those fringes we were relying on as our ruler rely on two things to be stable, not just one. They rely on the plate staying put. You have to have a very stable mechanical plate that you trust. But you also rely on the light. If the light changes wavelength, then the fringes will breathe in and out. And I was just thinking, well, stars are pretty close to lasers, aren't they? They'll stay the same wavelength. Well, of course they don't. Stars sometimes get a little hotter, they sometimes get a little colder. It's only by a few Kelvin out of a few thousand Kelvin, but that change in temperature of the star will cause the fringes to breathe, and the fringes on the sensor are my ruler. So, yep.
Your video is messing with us.
Is it
It's
back?
back.
All right. So I needed a way to somehow monitor the starlight at the same time. I needed to lock down the wavelength of the light, as well as locking down the mechanical stability of this diffractive plate. I needed to lock the wavelength of the light that was illuminating it to make my ruler stay. So astronomers know how to do this, opticians know how to do this. You build a thing called a diffraction grating, and then you get a spectrum. When you get a spectrum of the star, you can measure the temperature of the star, and you're all good again. You can then calibrate for whether the star got a bit hotter that day, whether the star got a bit cooler that day. You can return the measurement back to the precision you need. But the way we build a grating, and if there's any Fourier geeks in the room, this is a sort of a wow moment. The way we build a grating is you put a ripple across your, you rule grooves across your optic, and that causes diffraction lobes. So this is all very well. We've got our primary pattern. This is to make our point spread function to that lovely pizza. Now we've got our gratings to measure the temperature of the star. And what that looks like monochromatically is this. So we have our point spread function in the core, lovely big mess. Now we've got our side lobes, but that's monochromatically. If we look at what that would do polychromatically, it's doing what we want. We're getting blue light streaking through to red light here. We're getting a grating that's giving us a spectrum. But if you've ever done any optics, you just realized we built the world's worst spectrometer because there are two competing requirements here. In the core, we want the worst possible point spread function. We want this big messy thing. But out in the side lobes here, we want a nice clean slit spectrum. We want a very clean spectrum of the star. And you don't get a clean spectrum of the star when your slit looks like a pizza. You need to narrow down the slit to have a really nice clean spectrum. So these look like completely orthogonal competing demands on the optical system. On the one hand, we wanted the world's worst point spread function. On the side lobes, we need the world's best point spread function. And then this piece of complete Fourier magic occurred to, in fact, it was one of the opticians in my team. This still takes my breath away. If you flip the grading up every time you cross one of these major boundaries, remember these are steps in phase, 0 to pi on the primary mirror. You have this grading running along. Every time you cross one of these boundaries between pi and 0, you flip your grading upside down, and then you flip it back. You get this magical property where the primary beam inherits the nasty point spread function. All the odd orders of the pattern inherit this, but the even orders think you made a perfect telescope. It's just stunning. You get a diffraction limited first order while you still have a completely messy 0th order. And of course, you can then look at how that performs as a spectrometer, and it works perfectly. So now we've got a messy point spread function in the core, but a very clean diffraction limited side lobes. We can now recover the stellar spectrum. This is an injection recovery from an honours student from a couple of years ago, now at New South Wales Uni. But you can see we inject lines. These are known features in the stellar spectrum. So we can actually now recover the plate scale perfectly using this kind of hybrid diffractive pupil, we call it. I'm going to pivot now. So we've now got quite a lot of innovations stacked up one against the other, and we wanted to try and do a better and better job to exactly how do we mess up this telescope in order to get the best outcome. And this is where things, the mission that I'm building is going to be half made of software. And maybe this is the most innovative part of the whole thing, is the software that we've managed to build around these optical concepts. It's really incredible. So if you imagine a number of candidate pupils, you can mess up that this concept pupil I've been showing till now, this tri-spirals, was just a mathematical construct. But if you want, you can try to say, well, how should I make this to best affect my measurement? So if you wanted to go into the maths of this, and there are theory papers about it, in fact, the best pupil of all of these ones, and there's a bunch of candidate messy ones, and then an unobstructed, clean, what astronomers would say would deliver an airy disk pupil. The best one's this one, airy disk. And you can prove that mathematically from fundamental image theory, because you're trying to register something on a sensor. Then the flat parts of the image give you no information. It's only the slopes that tell you where something is. Under translation, a flat piece of the image is invariant under translation, but the slope will move. So there's actually a metric we can derive from an image like this called the gradient energy. How many slopes are there and how steep are they? The gradient energy is a proxy for how easily you can register something on a sensor. And the maximum gradient energy of any of these is the airy disk. And you can prove that that is the maximum and theoretically possible. So one would say from an information theory point of view, we should be going with an airy disk, none of these fancy pupils. But a student and a colleague of mine now in Brisbane, Ben and Louis, wrote this amazing code called Deluxe. And I'm not sure if you do any optics here, but even the principles underneath Deluxe, I think, are really amazing. What he was able to, one thing you're able to do with Deluxe is principle design. So you can design an optical system targeting some metric. Deluxe is written in JAX, so this is a differentiable language. And if you forward model something in Deluxe, you can then basically turn it around into an inference engine, and you can chase, because you've got derivatives, you can chase derivatives to whatever metric of merit you like. And if you ask the question, which of these pupils is better, what we care about is, so what Louis done here is he said, okay, I want the posterior, the final posterior for the separation of two objects on a sensor imaged with each of these systems. And the best posterior you can see here is the one with the narrowest full width half maximum. You've constrained that posterior better, is the airy disk. So this verifies that the airy disk, as a theoretician will tell you, with the maximum gradient energy, is actually the most registerable image of any of these. The other ones all have wider distributions for gradients. But when you add other errors in, so these posteriors now are calculated over the assumption that not only do we have photon noise from a perfect PSF, we've also got an unknown plate scale. That means that the magnification might have changed. We've got an unknown wavelength. Our wavelength of our star might have got a bit hotter, might have got a bit colder. There's a defocus going on in our telescope, and we need to infer all of these out of the same image plane. Now you can see that the posteriors we get from our featured pupils are much tighter than the posterior we get from the airy disk. So this, I mean, to me, as an old guard guy who hardly understands how to write anything in JAX, this is kind of revolutionary. We have kind of run a gradient descent to optimize these complicated shapes. And the merit function we're chasing is the actual science outcome we want at the end of a really big, nasty pipeline of inference. The metric is, this is the best pupil for measuring the separation of a binary star on the sky under the assumption of an unstable telescope with these Zernike errors, with this photon noise errors. It's really startling that you can even pull this off. So at the end of all of that, we ended up with thousands and thousands of candidate pupils. But these, you can see some commonality here. They sort of end up with this sort of bed of nails. You want lots and lots of sharp features, which helps you register where it is. But you don't want a single really bright sharp feature, because that gives you no information about the distortions in the telescope. So if you have a fairly complex pattern, which still maintains this very high gradient energy, you sort of have this optimum. So we ended up with, this was our final choice of pupil geometry. So now we need to build it. How do you actually go about making something like that? You could actually do what I described. You could make a mirror and you could grind down parts of it. And in fact, there are even special polishing machines that could even conceivably do that now, or lithography. What we've got instead is this amazing technology. This is our linkage with Leiden. They help us with the designs. The actual optics are fabricated in Japan, a company called ColorLink. But this is almost cheating, this stuff. You can basically deposit a phase volume hologram on a surface coating, and you can specify that to about 20 micron pixels, and you can write whatever phase hologram you want. And in fact, what they've done here is they've written a phase hologram that, when you shine a laser through it, has a point spread function that is the TOLIMAN logo patch. And you can see it's doubled because technical reasons, left and right circular polarization are deflected different directions. So left circular is up here, right circular is down here. But you can bespoke design a point spread function that looks like anything at all. It's really quite insane. So I'll show you maybe I should show you, where is it? Yeah, I'll come to that a little later on, but I'll show you the phase holograms we have. So this is what the final data frames will look like. We'll have our complicated pattern here in the middle with our binary star, which, because Alpha Centauri A and B are not the same brightness, you can see a shadow there that's a little fainter off to the side. That's Alpha Centauri B. Then in the corners of the chip, we get these diffraction limited side lobes, which are where we do our spectrograph. And at this point, the mission starts to confront challenges that are also about the engineering and how do we actually fly this and make it all work, and how do we downlink the data. This is a very large frame of data. We have to censor this data because we can't afford to download it all. So lots of practical mission challenges that come into play. So to try and inform some of this, we built TinyTOL, which is a little 20 millimeter, sort of 1 inch aperture optic. You can see this was the early, an early iteration of the ideal pattern. The latest one I'll show you in a minute. This was built and incorporated into a CubeSat, a 3U CubeSat that flew to out of the International Space Station in 2020. We all watched the video of this CubeSat being slung out of the deployer, and that was the last we heard of it. You never got any data back from that CubeSat. That was launched by the Quava group over in physics. But one of the cool things about it, apart from the fact that we actually got something into orbit, principle anyway, we saw it there, we didn't get data from it. But you can see this is this pattern, and you can see it's doing exactly what we dialed up here. You can see it's, the core has got this massive point spread function with the laser, the side lobes are diffraction limited, and we've got these lovely spectral streaks when we illuminate with polychromatic light. I'll do a quick. So after our little CubeSat failed, I called NASA up and they agreed to launch a little precursor mission instead for me. Nice of them to step in. So in fact, we have a mask on this telescope, which is in fact a diffractive pupil, which is why I've added it to this talk. I always carry an interferometer with me, so if anybody wants to see, this is in my intro, it was mentioned that I fly an instrument on the James Webb Space Telescope. Well, I'm sorry, but that's the instrument. It's an aperture mask, and when it is incorporated into the beam train, you can see this lovely star field. When you slot the mask into place, it sort of explodes into little snowflakes. It's quite beautiful, really. We haven't got all the way to the bottom of the rabbit hole here with understanding this data, but this could be used in the same way those diffractive pupils. You could use this as an image registration technology. Rather, what we're trying to do is to turn the Webb here into an interferometer. So we have separate sub-apertures inside the 6 meter primary of the James Webb. It produces a nasty looking point spread function like that. And the game is to try to use data like this to recover the coherence between each of these pairs of apertures to do interferometry with it. It's kind of a sort of an open secret that we're one of the experiments that really has had a lot of challenges aboard Webb. Webb's been this overwhelming, stunning success, but one of the things it hasn't done is really high resolution imaging science. And the reason turned out to be something we knew about before, but we kind of swept under the rug, and a thing called the brighter fatter effect. When photons land on a sensor like this, they don't stay put. And when enough photons accumulate in one pixel, they'll start migrating into neighbours, a thing called charge bleeding on them. We call it the brighter fatter effect, because the brighter something is, the more it bleeds. The more it bleeds, the more it seems to be fat. So this has been this nonlinear killer for anybody, not only the mask, but anybody trying to do high resolution science with Webb. And that code I showed you before is again riding to the rescue here. So not only is it a design code, but it's also a data analytics code. When you have this differentiable forward model that runs blisteringly fast, you can try and just solve for everything, and try and solve for simultaneously a model that forward predicts the brighter fatter effect as well as the astrophysical scene. So I don't have a lot of time, so I won't jump too much into that. But yeah, talk to us later about Deluxe. It's really remarkable. So here's our here's that pupil that I told you about, and it's now actually implemented for real. This is here in the room with you. This is actually what's going to fly, except that this one is printed onto a cheap substrate. The true substrates will fly are made of zero duo, and which is a special glass that is very stable against temperature. This one's simply on a piece of regular glass, but you can't see much until you see that now. Is that sort of working? Yep. Yeah. Doesn't look much from where I'm standing, but I hope it's okay for you. So when you view it through cross polarizers, you can see exactly that pattern. And just like I said, this this technology is amazing. Not only is there the primary pattern with the steps of the destructively interfering steps, pi and zeros, it's also got those ripples we need. Remember, we need the side lobes. And the ripples, remember, need to flip when they cross a boundary. So you can actually see the cadence flip upside down when it crosses. This is magnified of these primary boundaries in the pattern. And does it work? Yes, it does. So this is the point spread function we wanted, and it's the point spread function we got. And you can see these side lobes that are fraction limited, and the core is giving us exactly the pattern we wanted. So it's optics actually, Fourier optics just made easy. I'll just finish up with a few status slides for where we're at today. This is the telescope structure itself, the OTA, the optical telescope assemblage. Connor's had an awful lot to do with this. It's made by this company called AOS in the east coast of the US. It's a solid piece of silicon carbide with a primary mirror that's made out of silicon carbide. Chris Bettis has been doing most of the ray trace optical design to formulate the design. It's all going to be packaged into a 16U CubeSat, which is about as big as CubeSats ever get. It'll look a bit like that. This is being done by a Bulgarian company called Futuristic. There are some of the specs. It's got lots of downlink. Yeah, so this is actually under construction. We're all sort of, the telescope itself is being built. We're still waiting on the secondary mirror. One of the big things Connor has been doing is trying to make sure we can point accurately enough. Just about everything we're doing is at the boundary of impossible, I think. So in low Earth orbit, we need to point to better than an arcsecond, and we need stable pointing to. We don't need jitter to about an arcsecond per second. So these are all fine if you're, got a $10 billion and you're out at L2, or you're out at LEO and you've got 100 million even. But for, a couple of million in low Earth orbit, that's very, very hard. CubeSats just don't do that. So we've had to onboard a lot of spacecrafts, flight metrology, flight control into our science instrument. So Connor's been designing this yoke that allows us to put up with the fact that the spacecraft can't point well enough for us by actively gimbaling the telescope itself around its center of mass. So we have a tip tilt system pointing our telescope for us. We also care a lot about thermal control. One thing I like to say is that we've got to point better than Hubble, which is $2 or $3 billion, and we've got to be about as thermally stable as Gaia, which is $2 or $3 billion. We've got to do it all in low Earth orbit, and we don't have $2 or $3 billion. There are a whole bunch of thermal engineering that's required as well. We had an engineering student do this as well. This is Mark's work on his thesis a couple of years ago. Here's our telescope. It's a real thing. It exists. It's being built. We don't fully have all of the components yet. We're still trying to get everything polished. And here's where Grace has been working in the basement on a test rig. So these are a couple of parabolas. So there's a light source injecting. So we've got a parallel beam between these two mirrors that fakes up a starlight beam for us. So we can put our refractive pupil in the middle here and make sure it's doing what we hope it does. So yeah, Grace has been enjoying the journey about how to align off-axis parabolas, which is sort of one of the pieces of voodoo that opticians always blanch in fear when they hear. I'll finish up. I think I've kind of covered most of this. I'm probably at my time. I'll leave time for questions. So we need about 3 years of data. So that's why even the downlink is expensive, because you've got a data-hungry satellite, and if we don't watch it for 2 or 3 years, we won't get cycles of the star being dragged back and forth. So that's still another challenge. And despite how crazy it all sounds, we've actually inspired a bunch of follow-on or copycat missions, you could say. NASA had another one. They even called it TOLIMAN, which kind of annoyed me for a while. They've now had the good grace to change the name. It's called SIRIS. And they're applying for about, they costed TOLIMAN itself, exactly TOLIMAN, 20 million. I wish I'd had 20 million. But they've now they're putting TOLIMAN concept in called SIRIS there for a SPECS mission. There's also a thing called THEA, which is a European Space Agency, which is another follow-on mission. I'll just chuck up a slide of the team. Grace and Connor are here with us. Adam's kind of a de facto member here, but I'm not actually formally on TOLIMAN. And thank you for your time.
Peter, do we have questions for our speaker? Get us started. So you hinted at some of the fundamental limits, the noise floor on how much information you can get out in both the sort of the astrometric and in the radial velocity sense. What stops us from just capturing more data over more time and combining that over time to reach the signal to noise ratio?
For which one?
Both.
Okay. Radial velocity techniques hit a fundamental noise floor to do with the fact that the star is not stationary. It's got a seething surface underneath it, which is a nuclear reactor pushing all the stuff around. So because it's got a turbulent seething surface, the star itself has its own line of sight noise. And that noise floor is very hard. It's not even very white noise. It's got long-term, like when star spots come around, and it's got sort of long-term red components to it. So it's not simply so for radial velocity, that it's not simply a matter of building a better, more stable spectrometer. The noise comes from the star. People are talking about how to be predictive about that and to have a good model to back out the stellar noise. I think that's going to be a hard game, but that's possible. The fundamental noise floor I talked about for astrometry is almost the same thing, stellar activity. So when a star spot comes across, then if it's dark if there's a dark spot in the star over here, you'll think the star just jumped to the left a little bit, right? Because there's a missing piece of light over there. That is actually a much smaller noise floor, and there's an interesting reason why, than the radial velocity noise. But it does give you a noise for about about half a micro-arcsecond. And again, you could think about predicting that. If I saw a star spot go around last month, maybe the same star spot's going to go around next month, and I could try and understand that. But yeah, it's the intrinsic noise of the star that's sort of ultimately set some of those limits. But yeah, there are other noise laws too.
Thanks. Steph.
Great talk, Peter. Thanks. You're leading to many possible things to address along the way. Are there any remaining? What are the things that are keeping you away from start to kind of get this working and getting big?
Yeah, I mean, just the performance requirements in low Earth orbit are really demanding. We need really stable pointing. When you're in low Earth orbit, it's not. People tend to overestimate how nice and stable space is. You fly over deserts, you fly over the poles. The actual upcoming radiation from the Earth is a very large fraction of the radiant environment that you encounter. And even if you can try and be in an orbit where you're called sun sink, where the sun is at a constant vector from your spacecraft, you fly over regions of hot and cold, and that's going to change the conditions for the spacecraft. And I wanted, for example, in order to meet budget and timelines, we have this plate that's performing the work for us that's sitting out the front of the telescope. So that's going to be right out there where a lot of those thermal changes are worst. If I'd had another, $2 million or something, I would have actually carved those steps onto the primary mirror And then I would have had everything kind of much more stable inside the spacecraft. But you also have to meet timeline and budget, and you have to go fast. I mean, that's one thing about working for the Silicon Valley guys. They're like, this is disruptive space. This is not old school. This is not old school sort of space agency space. So there's this whole concept that we were trying to meet from them, which is go fast and break things. And so that actually has some conflict with, what is it, fast, cheap, good, choose two. So we certainly got cheap. We didn't really get fast. I hope we're going to be good, but yeah, I think we're flying a lot of things that an orthodox agency would regard as very low TRL.
Would a different orbit help, or is that on?
A geo would be awesome, but any low Earth orbit is going to be pretty hard for us. I mean, people don't do what we've tried to do. The Gaia spacecraft, if you really want to do astrometry and you've got space agency budgets, you have no moving parts on your spacecraft. So you throw away all of the reaction wheels, you throw away all of the gyros. Gaia, which is this, so that's the sort of state of the art for contemporary astrometry. That measures the entire sky. It's pretty stunning. Gaia measures 1 billion stars, 2 or 3 billion by now, and it does them all to within a factor of 10 of where TOLIMAN will get with 1 star. So it's about 10 micro-arcseconds, 15. So Gaia's nearly there. Factor of 10, okay, it's not there, but it's in the zone. And it's doing that through 1 billion stars, right? That's pretty impressive. I'll try and do that for 1 star. But Gaia does that by having no moving parts. They basically made Gaia, it's sort of, I think it's about 2 meter diameter block of silicon carbide. And they assembled all the pieces and they put it all in an oven and they melted it so that all of the silicon carbide and boundaries ran into each other. So it welded into one block of silicon carbide. And then they pulled it out and they're like, oh, damn, the mirrors all slumped because, of course, you had it in an oven. So they then had to repolish the mirrors. But you don't only have to repolish the mirrors because you need to polish an optical surface that's now inside a silicon carbide cage. They had to invent special polisher things on arms that went in and polished surfaces. And these are 1 meter mirrors. So this is where $2 billion goes, right? That's why this is and the whole thing is spinning on its own axis at a very distant orbit. It's not in low Earth orbit. So it's doing things in a big space agency way with shock and awe. Amazing, but yeah, you don't do that for the university class budgets.
One more question. You're first at the front.
Thanks, Peter. Just to follow up on that, I guess you are in low Earth orbit, you have all the vibration, you have moving parts of the spacecraft, gravitational effects, atmospheric effects, whatever. How big of an effect is that going to have on science output?
I mean, I think as long as I could get, I think the vibrations and things, I hope that they're all manageable. I mean, there's so many things that matter. The relativistic drag of the light, because you're moving with respect to the scene, and the scene will then be, offset at a different angle than you thought it was. But even though you're only measuring a binary a few arcseconds across, binaries not uniformly being dragged in the same direction. So you've got to do relativistic corrections. There are many, many things that come to bite you. The scale of the precision you need is really insane. Every second, the binary orbit moves by more than the signal you're looking for 6 months, right? So there's a star railing around the other star here. It's got an 80-year orbit, but it's going. You're looking for about a 100 kilometer, 200 kilometer wobble, and it goes, 200 kilometers a second. So you're following the locus, and you're looking for a perturbation on a locus. So the timing with which you download the frames matters. And if you try to add frames up, you're no longer adding frames up where it was at the same place with respect to the precision you need. So I think there are lots and lots of challenges. I'm not sure what the worst ones are. Connor, do you have any?
Well, from memory from what Maxwell's work was on it seems like there are three kind of regimes. It's our higher frequencies, so higher than our cap rate at 10 hertz. It's like around 10 hertz, and then less than 10 hertz. So you'll start to see the work of drag. And so it seems like either side of 10 hertz is quite manageable, either through the tip tilt system that we've shown, or fixed in post, so being able to model it in software. But the ones around 10 hertz are a bit of a concern. That's what I'm trying to manage, I guess, on forward. Yeah.
All right, folks, I think we'll call it there. If you have more questions, you want to talk more about this, Connor has joined on here to do a PhD, so he'll be around for a bit. We'll get to see much more of Peter also.
Yeah.
So please join us in thanking our speaker today.